My name is Minko, and today I'm going to be talking about how we can write faster Angular applications. So let me start with just a couple of words about me. Currently, I'm co-founder and CTO at Rime.com, where by using virtualization in the browser, we are trying to help you to build more consistent and scalable workshops and corporate trainings. In my spare time, I'm doing a lot of open source. So I've been a former member of the Angular mobile team, where I was helping to build infrastructure in order to develop easier progressive web applications with Angular. I'm also co-author of the Angular style guide, where I had the chance to work with John Papa, Igor Minar, and Ward Bell. And currently maintaining Codealyzer, which is a tool for static code analysis for Angular applications. And of course, Angular Seed. So I've also written some books. Switching to Angular is the latest edition of my book. So if you're just switching from AngularJS to Angular or getting started with the framework, this might be a good fit. Today we're going to talk about runtime performance. Usually when we're discussing single-page applications, we're either talking about performance optimizations related to the network performance or to the runtime performance. The network performance usually involves just reducing the number of HTTP requests or reducing the payload that we're transferring over the network. And there is a lot of research going on in this direction. For instance, we have the Google Closure compiler team who are constantly reducing the bundle sizes by performing more efficient dead code elimination or minification. We have different compression algorithms. We have the Webpack team with similar goals. And on top of that, we have the Angular CLI team who are combining best from both these worlds in order to provide very well encapsulated build. However, regarding runtime performance, there is not much going on. And everything is in our own hands. So we cannot take advantage of some magical tools which are just going to make our applications run faster. And today that's what we're going to discuss. In general, there are a variety of ways to approach this problem. Today we're going to focus on some more generic approaches which are applicable not only to Angular, some of them, but also to other technologies as well. In order to illustrate these optimizations, I built a very simplified business application. In this app, I tried to incorporate as many of the performance issues that I faced over the past couple of months working on Angular application as possible. So we have some terrible experience initially, and we're going to try to incrementally improve it. Here is the application itself. So we have super simplified application, business application, where we can just enter new employees. We can list these employees and calculate some value for them. In general, we have two lists of employees for a sales department and for an R&D department. In both of these lists, we can add items, and the items which are already existing, they're being visualized in this list right here, where we can see there are names and some numeric value. We can think of this numeric value as, let's say, performance of these employees. We have also the text input, where we can enter new employees. So when we enter an employee, we can just take its performance, like its numeric value from somewhere. After that, compute something with our business function and visualize this on the screen. So that's the application. And here is its simplified structure. This is static component tree. And we can notice that we have an app component, which wraps the entire application. We also have an employee list component. In fact, two instances of it, one for the sales department and one for the R&D department. Here is the template of the employee list component. So the important things inside of this template are that we have an input. We're using the banana in a box syntax here in order to establish two-way data binding between the label property declared in the controller of the employee list component and the text box, the material design text box. We're also iterating over the individual employees that we have in the data array. And for each individual employee, we are rendering a material design list item. For each material design list item, inside of it, we are rendering the name of the employee and also calculating the numeric value by using a calculate method, which is declared inside of employee list components class. So here is the class itself. It has a few important things inside of it. So first, it doesn't hold state. It gets the state as properties, as inputs. And it receives this array of employee data from its parent component. So we can conclude that our app component passes some data to the employee list component, and the app component is something like a container component in the context of Redux. We also have this calculate method, and its only purpose is to delegate its execution to a Fibonacci implementation. Fibonacci doesn't sound practical at first, however, it has some very important properties. First of all, we are already familiar with this, so I don't have to introduce a very complicated business computation, which is domain specific. So this could be replaced with, let's say, standard deviation or like anything which is meaningful for our application. Fibonacci makes sense because we can implement it in a very inefficient way. So we have two recursive calls here, and we're going to recompute the same value for a given nth Fibonacci number all over again. So we're slowing down this application here a little bit artificially in order to stress on the optimizations even further. In general, we can conclude that our application has an app component, and inside of it has two instances of a list component. For each entry in the list component, we're going through a very heavy computation, and that's pretty much it. Let's see how this behaves with some real data. So here we have two lists of items with in total 140 entries. And with these 140 entries, here is the typing experience that the user is going to have. We are typing. So yeah, it's not the most impressive one, definitely not something which our users are going to enjoy. But why is it that slow? We can profile this pretty easily. So just opening the Chrome DevTools tool, we can open the performance tab. We can do some performance profiling and find out that obviously our Fibonacci implementation gets invoked very often. And in fact, in order to see how often exactly, we can just add a log statement inside of the calculate method. Here is how often this method gets invoked. So quite often. In fact, every time when the user presses a key on the keyboard, we're going to trigger the change detection for the entire component tree at least twice, once for key up and for key down. So we are recomputing all the already existing numeric values which we have computed every time when we try to type a single letter. Here is how this looks in terms of the component tree. So here we have the already rendered component tree, so dynamic component tree, and we have the app component. So every time when the user presses a button, we're going to invoke change detection first in the app component. Right after that, because Angular's change detection is performed just depth first traversal, we're also going to invoke the change detection in the employee list component. We're going to go to the employee 1, after that employee 2, and so on and so forth until we reach employee n. And for each one of these employees, we are going to recompute their numeric value. The same is going to happen onto the right-hand side of the component tree. So that's quite inefficient. Basically, every time when the user presses a key on the keyboard, we're doing all of these computations. In general, we don't want to recompute the numeric value for each individual item in the array. We would want to do that only when we get a new array, right? So when the app component passes a new array to the employee list component, we would want to recompute the numeric values for the employees. Do you have any ideas for how we can do that? Yes, on push. That's a very good suggestion. So yeah, we can use on push change detection strategy, and by using it in general, we're just going to enforce the change detection to run only when the component gets new inputs. So when our employee list component gets a new input, and Angular is going to determine that by using a reference check, we're going to update our component, like perform change detection inside of it. So if we have a component tree, when the root component of this component subtree receives new inputs, we're going to run change detection in the entire component subtree. We're going to see how this looks visually in a little bit. But before that, in order to make it even more obvious, let's just for a second pretend that our employee list component was a function, because we talked about functional programming already during the keynote. So our function now has arguments, which we can think about them as the component's inputs. And the rendered result on the screen is the actual result of the function. So here we're assigning reference to the employee list component, which now is only a function, to the constant f. We also define data, which contains only a single employee. And here is what we do. First, we pass arguments. We invoke our function with its initial inputs. And here, Angular is going to perform change detection. because the previous value of the input was undefined. So when Angular compares data with undefined, it's going to figure out that the input has actually changed. When we push a new item into the list, however, we're going to have the exact same reference, which means that we're just going to modify the data structure pointed out by the data constant. When we invoke our function with this data, basically it is going to be the exact same data, which is already a value of the data input. So Angular is not going to perform change detection at all, because after reference checks, it is going to determine that we have the same input. However, if we copy the entire list, we're going to trigger the change detection because we're going to get a new reference. This means that passing a new reference is going to trigger the change detection. Does this mean that every time when we want to trigger the change detection, we need to copy the entire array? Well, that's going to be extremely inefficient because of several reasons. So first of all, it's going to be extremely memory inefficient. We need to copy the entire array every time when we want to trigger a change detection, and after that we need to deallocate this memory, so the garbage collector is going to automatically do that. Second of all, it's very computationally inefficient. It has at least O(n) complexity, so it's least linear complexity. So we definitely don't want to do that. However, we can use something more efficient in terms of both performances, so in terms of both aspects. We can use something like Immutable JS. It's a collection of different immutable data structures where we get two very important properties. We cannot modify any of the existing instances of the data structures. We can just, by invoking an operation which intends to mutate them, get a new reference to the data structure with the modification already applied. And second of all, we're not going to copy the entire data structure, because we are only going to apply some structural sharing inside. So the new instance of the data structure is going to reuse as much as possible from the original instance as possible. And here is the refactoring that we need to do. So there are a few places where we need to do some refactoring. First, in the add and remove methods, where the difference is going to be that when we apply unshift, for instance, to push the item into the beginning of the array, of the list, we are going to get a new list. Same for the remove method, where when we apply splice, we're going to get a new list. And of course, we need to change the reference to the list, because otherwise we would not be able to notify the employee list component that its input has changed. So we need to assign the result out of add and remove to the list property of the app component itself. So let's see how faster we are. We did some crazy optimizations with onPush and used some functional programming methods with immutable data structures, and we might expect like some great improvements eventually. Well, it doesn't look that great. It might be a little bit faster, but in fact, it's not very friendly to the user as well. It's very poor user experience again. In order to measure how faster we got, I wrote a bunch of end-to-end tests and run them by using bench press by Angular. So I got some performance benchmarks out of it. And here is how much faster we got. So we are about 3 times faster, at least twice faster, but we are still very slow. And here is why. When we start typing something into the inputs of the sales department, we get the change detection triggered again. The good thing is that this time the change detection gets triggered only for the sales department. We're at least not triggering it for the R&D department, but still it's not necessary because the numeric values for none of the employees has changed. Here is how this looks in terms of component tree change detection triggers. So every time when we press a button, we're going to invoke multiple times the change detection in the app component, in the employee list component, and all of the individual child components of the employee list component itself. However, this time, at least we're going to skip the employee list component for the R&D department. Well, that's good, but still we haven't gotten any new data structure with new items, so we haven't invoked any of the mutation operations for the sales department. So why the change detection gets triggered? Well, this is caused by not very well documented characteristics of the onPush change detection, which you can find in the end-to-end test for the Angular core, where the change detection also gets triggered when an event inside of a given component with onPush change detection happens. So yeah, in order to fix this, we need to do some refactoring. The good thing about this refactoring is that it is also going to improve our separation of concerns and make our component tree more coherent. So we can just decompose our employee list component to name input component, which is only responsible for just holding the current value of the input and after that triggering an event. And to the list component, where we're going to move our calculate computation, and also we're going to use on push change detection there. So here is the user experience afterwards. It's so much faster. And here is what happens. So when the user presses a single character on the keyboard, single key, the change detection is still going to be triggered in the app component, unfortunately. It is also going to get triggered in the employee list component for the sales department and for the R&D department. Fortunately, this time we're going to skip the change detection run in the component subtrees which root the list components. That's because they have on-push change detection and the events are happening in the scope of the employee list component, which is a parent component of the list component itself. So we can ignore the change detection there. And here is the typing speed improvement. It's so much better, yeah. 100 times faster. However, we're still not good enough. So we're going to do some more optimizations along the way. One of them is for adding items. We can notice that when we add an item, the change detection still gets triggered, and that's obvious because when we push an item to an immutable list, we're going to get a new list. We're going to pass it as input to the employee list component, which change detection is going to get triggered. So here is how this looks visually. We start typing something, which triggers the change detection in the app component and the employee list component. Right after that, we add this item into the list, which triggers the change detection in the list component, and also in its children. Although we have computed the numeric value for E1, E2, and so on until En, we're still recomputing it, although it's not necessary. In order to fix this additional recomputation, we can take a look at our function. So we already talked about pure functions today, and Fibonacci is one such function, which is basically a mathematical function. And the good thing about Fibonacci is that it is very close to what we would eventually want to use in our business computations. For instance, the standard deviation function is another pure function. And all of these pure functions, they have two very important properties. So they don't produce any side effects. This means that we're not going to send any network request over the network inside of this function, or we're not going to log anything onto the console or do whatever. We're just going to compute the result. And also, we're going to get the exact same result when we evoke the function with the same set of arguments. So yeah, in the world of functional programming, these functions are called pure functions. And the concepts actually are quite important, because in Angular we have pure pipes and impure pipes. The pure pipes and impure pipes, they are usually used for some kind of data processing. The pure pipes specifically, they just usually format data. That's what they're at least what the pure pipes in the core, Angular core, usually do. For instance, an example for a pure pipe is the date pipe. The impure pipes, they just hold some state internally, like the sync pipe in Angular. And the difference between these two is that Angular is going to execute a pure pipe only when it detects that its argument has changed. In general, Angular treats expressions with pure pipes as referentially transparent. This is a concept from functional programming, which is actually something quite simple. And in order to understand it even better, we can take a look at the code which the Angular compiler is going to produce for a given template, which uses pure pipes and impure pipes. In this case, we have the birthday date, and we apply to the birthday the date pipe. We also apply an impure version of the date pipe, and here is what the Angular compiler is going to produce. It doesn't look very readable at first. The good thing is that we don't care about the cryptic characters in the beginning. They're mostly for making sure that we as developers don't use these imports. So here is what is actually matters. In the first case, Angular is going to produce this check. This underscore CK is actually a check, where Angular is going to compare the current value of date, of birth date, with the previous one. And if it's a different value, then Angular is going to invoke the transform method of the date pipe. Otherwise, it is just going to return the previous result, which it has already cached. In the second case, Angular is always going to invoke the transform method of the impure pipe. So that's basically the difference. And that's what refresh transparency in general is about. This means that a given expression is not going to change its semantics if we just replace the expression with the value that it purpose. The expression should have very insignificant side effects. So yeah, that's the calculate pipe, and that's how we can encapsulate our business computation inside of it. We can just delegate the execution to Fibonacci, and that's it. And we need to modify our template a little bit. So we just need to drop the calculate method and instead use the pipe. After we bench press this, we're going to find out that it looks not that slow anymore. So this is another end-to-end test. We just add an empty employee and removes it afterwards. And here is the performance improvement. So about 100 times or more improvement again, only by using pure pipe instead of directly invoking a method declared in the controller's body. So far so good. We have two more optimizations to apply. The first one is optimizing the initial rendering performance of our application. Let's try to render our application and use 1,000 items inside of it. Of course, this is not something that we would want to do in real life. We may decide to use virtual scrolling or pagination or something. However, we're going to optimize in a slightly different way. So now imagine that we have applied a bunch of optimizations for our application. We have removed all the dead code that it has, and our bundle is 50K. We download it from the network for 100 milliseconds. Well, still, the user is going to need at least 8 more seconds in order to see something meaningful on the screen. So although we optimized our network performance a lot, although we did that, the computational performance is still horrible, and the user is going to still have horrible user experience. So we need to figure out how we can optimize this a little bit. Because in this case, our initial rendering was after 9.5 seconds. In order to fix this a little bit, at least to improve it, we need to take a look at our data. In this case, we can see that our data has duplicated values. So we have Fibonacci of 27, 28, and 29. Although we apply some kind of caching with pure pipes, we are recomputing the same values all over again. And fortunately, we have samples from a very small range. A solution is just to apply some global caching, because the pure pipes, they're just cached in a very local cache, only specific for this place, for this expression where the pure pipe actually is. We're going to see what the difference between real actual caching by using memoization and pure pipes is in a second. So the memoization that we're going to apply right now, or just global caching, it's possible only for pure functions. And here is how we can apply it, actually quite simple. So we can use lodash.memwise, invoke memwise with our function, which is going to produce a new function. Inside of it, memwise is just going to create a cache in terms of a map. And it is going to associate on each invocation of the function the results that we are getting as inputs, actually the inputs or the arguments of the function itself with the result that the function produces. And yeah, that's pretty much everything that we need to do. And this is going to boost our performance a little bit more. So previously it took 9.5 seconds. This time it took about 3 seconds less, which is not that bad for such a very small optimization that we did. And here is the difference between the pure pipes that we previously applied compared to memoization. So with pure pipes, when Angular sees that we want to invoke calculate of 27, it is going to delegate the execution to Fibonacci of 27, which is going to produce a result. The second time, when it sees the pure pipe, it is basically going to do the exact same thing, because the cache is only local for the place where this expression occurs. The same is going to happen for the third result as well. However, the next time when Angular performs change detection, if we haven't changed the argument of calculate, Angular is not going to recompute this result. So this means that we optimize the change detection runs for every next tick of the change detection by using pure pipes. However, with memoization, things are going to happen slightly differently. First, we're going to invoke calculate of 27. We're going to delegate this to Fibonacci, going to get the result, and create a cache entry for the result. So we're going to associate 27 with the result that Fibonacci produced. And we're going to reuse the same result for the next invocation of calculate of 27. We're going to do the exact same thing for the third result. So this is going to save us a lot of runtime. In general, we can notice a pattern right now. On conceptual level, the on-push change detection and the pure pipes, they are kind of similar. They're both referentially transparent. And if we think of the component tree as an expression, because in general it can be represented with something like an AST, we can apply referential transparency optimizations there as well. However, this is only valid for the last inputs of both the on-push change detection components for their inputs and for the arguments of the pure pipes. So now let's try to do a little bit better. This is a little bit more advanced optimization, so we're going to take a look at some internal Angular APIs. If you're not completely familiar with them, don't worry. I'll try to explain them as in-depth as possible. So about 90% of all the requirements in software development are that we need to visualize a list of items. And in Angular, we use the ng4 of directive for this purpose. So let's see how we can optimize it for our specific case. Here is how it works. It has a constructor which accepts as argument an object of type iterable differs. And here is how the iterable differs actually looks. It is just a class with a constructor and a find method. In the constructor, it accepts a collection of iterable differ factories. And its find method is going to accept as argument just a collection. Just whatever collection. It could be a binary, like a binary search tree, or a list, or a map, or whatever. In this specific case, it's not going to be a map because we have separate key value differs for this purpose. After the iterable differs accept this argument, they're just going to run a loop over all the individual factories that they have, and they're going to check whether one of these factories supports the data structure, the instance of the data structure. If they find such factory, they're just going to return it. And that's it. That's everything, what happens. So here are three more interfaces that we should take a look at. There are the iterable differ factory, which has the support method that we just described, and also has a create method, which accepts a track by function. This might be familiar to you from the interface of the ng4 directive, where we have track by function as well. And the create method returns an iterable differs result. The iterable differ is just an abstraction which accepts two data structures. It accepts one data structure, and it holds some state internally. So in general, its purpose is to compare two individual instances of a data structure. If we have data structure A and data structure B, the iterable differ is going to return the number of differences between these two versions of the data structure. So the number of items which have been added to A in order to get B, the number of items which have been removed from A in order to get B, and the items who have changed their places. And finally, we have the track by function. We're going to take a look at it in depth just in a little bit. Before that, let's see what the relation between these individual concepts is. So we have the ng4 of directive, which gets the iterable differs injected as arguments to its constructor. It also uses the iterable differ in order to find out what is the difference between the current object we are iterating over compared to its previous value. And we also have the track by function. The iterable differs, they use a collection of factories, which, on the other hand, produce an iterable differ, which uses a track by function in order to find by what characteristics of the individual items in the collection we're going to compare the items. And here is how the ng4 of directive uses the differ. It's just going to invoke a diff on top of the current value of the collection that we are iterating over, and it is going to compare it to the previous version of the data collection itself. So if we have changes, we're going to just apply these changes to the DOM. And that's it. So let's see how this works with the iterable differs and with a specific track by function. We have a track by function, in this case, which returns the ID of given item. And here we have two collections. We have collection A and collection B. They are both lists, and they contain just items. So first, the iterable differ is going to compare the first element from A with the first element from B. And since the IDs of these two elements are the same, the differ is going to conclude that these items are identical. In the second case, the same is going to happen. Notice we have different titles, different names here for the employees. Well, the differ is not going to care about them at all, because it is only going to care about their IDs, and they are the same. However, if we have different IDs, the iterable differ is going to conclude that these items are different. So it is going to produce a result saying that the last item from A have been removed and has been replaced with the last item in B. So after that, ng4of is just going to render the difference. But notice that the iterable differ checks from the outside whether the data structure has changed or not. So it uses it as a consumer. But the data structure knows best whether it has changed or not. So what we can do is implement a custom data structure inspired from another functional programming concept that we're going to mention in a little bit. Inside of this data structure, we're going to keep track of the changes which happen to it. In this specific case, we're going to use a linked list because it performs slightly better compared to array. And we don't need random access to individual elements, so that's fine. And we're going to decorate the Immutable.js list. And when we modify this Immutable.js list, we're going to just push the change which happened inside of the data structure, inside of the list of changes. In this specific case, when we unshift a value, we can have different behavior. But inside of the unshift function, we know exactly what this behavior might be, so we can just push the changes into the result. So we are applying basically here the decorator pattern, since we're decorating the immutable list, and we are also implementing the iterator pattern in order to allow Angular to iterate over this data structure. So we built a data structure which is optimized for Angular. And here is a differ for it. Already it works with Angular. However, we are not going to get better performance if we use the default iterator, the default differ. We can use this special differ, which with a constant check finds out whether the data structure has changed or not. So we don't have to iterate over it anymore. What we can do instead is just access the changes property, and that's it. This requires a little bit of refactoring, but not significant one. So we just need to extend the current set of iterable differs, and that's everything. In fact, this data structure, it is inspired by persistent data structures, which is a concept from functional programming again, where we can do some crazy stuff, like we can do time traveling, we can fork some universes. It's pretty cool. So I would recommend you to take a look at this. And here is the performance improvement. We have about 30% improvement, which is not bad. So in recap, we can say that on-push change detection strategy might not behave exactly the way that we expect every time, because it is going to trigger the change detection for given component subtree, not only when the inputs of given component change, but also when an event inside of this component happens. Also, we saw what the difference between pure pipes and memoization is, how we can apply what the difference in the caching mechanism actually is, and how we can take advantage of pure pipes in order to improve the performance of our app. We explained also purity and referential transparency, which are two very common concepts from functional programming. And finally, we explained how differs and track by function works, and how we can only reduce the performance of our application, in fact, by using different track by function compared to the default one. So yeah, we can conclude that unfortunately there is no silver bullet for optimizations, for runtime optimizations. There is just, we need to apply very deep understanding of our component tree, and also understand our data that we're working with in order to apply specific to our application optimizations and benchmarks. And of course, we need to get inspiration from computer science constantly, because that's a great source of wisdom. So here are a few links where you can get more in depth for these topics. We have Angular's on-push change detection strategy in the first article. We have pure pipes and referential transparency in the second one, understanding differs. Also, a slightly more extended version of the Angular performance checklist, where there is more information about how we can apply custom change detection behavior by using the change stuff outside of the Angular zone, and one more video on similar topic. So thank you very much for your attention.
And now the questions time. You can ask in Russian, I will try to translate. Ну что, хоть один вопрос. Давайте, ребята. О, господи.
Yes, yeah, we can. It depends, because we create a new entry in the map for every individual input. So if our function gets far too frequently invoked with different arguments, we can just run into some problems. However, yeah, so we can apply different strategies in this case. We can just use something like least recently used and just put some limit of our cache. So, yeah. And it also depends what the keys in our cache are, because if we are working, for instance, with some reference types, we may run into some other problems as well. So,
next question.
You had some changes collected in one. You had one changes collected in one type. I failed to remember its name, and you will accumulate those changes in time. Who is responsible for clearing them?
Yeah, the differ is responsible for this. The data structure accumulates the changes into the linked list. After that, the differ takes the current list of changes, and after that resets its value. So on the next iteration, it can find out the next set of changes.
Isn't it looking a bit dirty?
Yeah, that's how, well, it has two issues, in fact. And if you take a look at the implementation of the iterable differ in the Angular core, these issues kind of persist. Although there are only theoretical issues, they're mostly related to violation of the single responsibility principle. This differ, it has two responsibilities. First of all, it needs to find the difference, and also it is used as iterable differ records, so it also contains the number of records which has changed. This is very convenient for this purpose, though, because it performs some good optimization. Otherwise, it may look a little bit dirty, yeah.
Thanks.
Hi. You were talking about performance. I'm not too much familiar with Angular and front-end, but how easy is it to implement some monitoring of your production? So measure what is going on your production code with Angular and find if something is wrong.
Yeah. Okay, I'm going to follow up just to, for the first question, it can look dirty because of the shared memory, because of the shared changes array. However, you can also use the internal types, which is just going to drop, going to improve the encapsulation a little bit. Regarding your question, I have usually profiled my applications in development, and that's how I usually do that. However, you can do that in production as well. You mean how you can profile the runtime performance of your users, right? You can eventually use some of the performance APIs in Chrome. They are not going to reduce the performance in production too much. And after that, you can have some logging service, which is just going to send the results to somewhere on the back end. But I don't think there is a standard mechanism for doing this.
Any more?
Hi. Did you try to measure it versus some other data flow strategy, for example, like RxJS using NNGRX with store and Redux?
So Yeah, we can run in different. Well, you mean mostly the runtime performance when using NGRX for this purpose? Yep. I see. I haven't done profiling for this. You can hit different performance issues there. Variety of performance issues. You just need to do profiling specific to your application itself, and right after that conclude what makes sense for you and what doesn't. Usually the performance issues with the Redux model are related to this frequent change of the global store, which passes the properties after that along your deep component tree, which may be not very efficient in all cases.
Okay. Other questions? Okay, I will ask one question. What do you think is the future of the change detection and the whole things in the Angular? Because, for example, in the React, we have a lot of the good practices to the data flow, etc., etc. What do you think? Will Angular take some patterns from the another frameworks?
Yeah. So there is already some work in this direction. You can notice that in the latest release in Angular 5, version 5, the zones are already optional. So there is some work in this direction which is going to allow us to trigger the change detection manually. And eventually at some point, the change detection may get slightly closer to the manual triggering which happens in React, for instance, with the manual states change. Like we're explicitly setting that the state of given component has changed by using setState. So now we can do something like this with Angular with a little bit more boilerplates by not using zones at all and using change detector ref and mark for changes. In future, we can get some more syntax sugar on top of this in order to allow more custom control of the change detection with better syntax.
Okay, thanks. Больше вопросов нет. Thank you very much, Minko.
Thank you.